All right, everybody, let's go ahead and begin going over this warm-up. So the main problems I want to focus on for this warm-up are questions 3 through 8, since these are the types of questions that you will see on your quiz next class. But we can begin by looking at questions 1 and 2, which is an application of percentages. Now, this is something that you guys might have not seen in a while, but let's take a look at it. So it says Danny goes to Costco. The total cost of Danny's purchases before tax is $200. If the sales tax is an additional 8%, what will be the total amount that Danny will need to pay? There are two different ways to show the final answer, the cost. Now, as I walked around, I did notice that you guys were able to translate this percentage, this 8%, into a decimal. So that is what you want to do regardless of any approach that you decide to take, is you want to translate that 8% and make that a decimal so that you can go ahead and multiply. Now, approach number 1 is probably the one that takes longer, but it's the one that most people did. So approach 1 is, okay, it's figuring out, well, what is 8% of $200? We want to figure out the tax. Now, 8% of $200, this statement here does have some math involved, of course. 8%, we are going to convert that to a decimal. 8% becomes 0.08. And the word of is a special word because the word of in mathematics means multiply. So this is 0.08 times 200. Now, 0.08 times 200 gives you $16. $16. This means that if Danny spent $200 at Costco, 16 would be for tax. Now, that's not the final cost. This is just the tax. The final price is the amount of, the initial $200 plus the tax, which is 16. So the final out the door cost would be $216. So this is approach number 1, where we are computing the tax individually and then we're adding it to the initial amount. Here is the second approach, and the second approach is easy because it's a singular step. But the second approach is, well, we know that 100% of 200 is itself, right? Like 100% of $200 is the original amount, but you're paying extra. You're paying an extra 8%. So in reality, you're not paying 100% of the amount. You're paying a total of 108%. So you're trying to figure out, well, what is 108% of $200? This is the second approach. 108% of $200, because this is the final amount. It's 100% of the amount you're paying, which is the 200, plus the 8% that represents the tax. So you convert this to 1.08. 1.08 times 200 gets you 216. And this is done, same approach where we are calculating the tax, but in the first method, we are doing it separately. We're calculating the tax separately. The second method, we're computing that tax, or we're adding that tax in to the original amount. Regardless of the approach, you still get $216. Okay? All right. Second problem, you're interested in buying a sweater that costs $60. You have a coupon for 25% off. How much will this sweater cost? Once again, two different ways of showing this. First method is the long way, but it's probably the easy one. And that would involve figuring out what the discount is and then subtracting it from the original amount. So that would be kind of like a two-step approach. So it's figuring out, well, what is 25% of 60? Well, 25% of 60, that would be 0.25 times 60, which equals, this is 15. So 15 represents the discount. So discount is $15. We would have to find the final amount by subtracting 15 from the original 60, which is going to give you 45. So $45 is what you end up paying out the door. If you notice, the first step was figuring out what the discount is. The second step is subtracting that discount from the original amount. Here's the second approach, which is going to be similar to what we did earlier. Now, 100% represents the total original value, but you're not paying for 100% of the original value of the item. You're not paying the $60. You have a 25% off coupon, so you're not paying 100%, you're paying 75% the price of the item. So instead of figuring out the discount separately, you can figure out the final price by figuring out, well, what is 75% of $60? Right? Once again, it's 75% because you have already factored in that you're not paying 100% of the original value. You have that 25% that you're taking out. So then we convert this to 0.75 times 60, and in a single step, we get our solution of $45. So 75% or 0.75 of 60 times 60 is equal to 45. Okay? All right, so these are the two different methods, the two different ways of finding the final solution. All right, then we jump into evaluating the exponent. So now we are going to use a lot of the rules that we talked about in lesson 4.00. We won't always need to use them, but oftentimes, if there's a lot of exponents, top and bottom, wherever, then we will need to use them. But for the first one, we don't need to use any exponent rules. This is a simple order of operations problem. You need to follow PEMDAS to solve this problem right here. We start with, obviously there's no parentheses, so we can cross that out. We start with the exponents, and exponents would be 3 to the 4th. Now, 3 to the 4th, if you wanted to expand this, you could. I won't in this case. 3 to the 4th is equal to 81, so that we have 10 times 81. Then we go ahead and move on to the next step. The next step is multiplication, so we multiply these two numbers. 10 times 81 is equal to 810. And of course, we stop there. There is no addition or subtraction to take care of. So for this first one, we get a solution of 810. All right, as we move on to number 4 in this case, now we do have some of these exponent rules that we need to refer back to solve this. Now, one of the biggest concerns here is that we have 2 to the negative third. This is going to require us to use the negative exponent rule, or negative exponent, I'm going to write NE rule, so you guys know which one I'm referring to. Once again, NE rule represents negative exponent rule. This means that you need to clean up 2 to the negative third by taking its reciprocal. That will become 1 over 2 to the positive third. And of course, you still have the 4 that stays as a 4. So we have 4 times 1 over 2 to the third. This becomes 4 over 2 to the third. At this point, we can clean up 2 to the third. What is 2 to the third equal to? It's 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. So this becomes 4 over 8. How can I reduce 4 over 8? There's a common factor. What is a common factor between 4 and 8? It's 4. 4 is a common factor. 4 goes into 4 once. 4 goes into 8 twice, giving you a solution of a half. Okay? As you can see, the only rule that we had to apply here was the negative exponent rule. And once again, the negative exponent rule is going to require you to take the reciprocal. Okay? All right. This one is a lot of steps, but we're going to do, focus on the numerator, then the denominator, or vice versa, one step at a time. If I choose to focus on the numerator, this right here, a power raised to another power, is going to be the power rule, PR. Actually, I'm just going to write it out, because then you're going to get it confused with the product. So this is power rule. Okay? Power rule tells you what? The power rule tells you that if you have a power raised to another power, you multiply the exponents together. So let me go ahead and clean this up for you. 5 squared raised to the 4th is going to be 5 to the 2 times 4 power, which is equal to 5 to the 8th. So we have 5 to the 8th on top. That is your numerator. Now let's focus on the denominator. 5 to the 0. This is the 0 exponent. ZE rule, zero exponent rule, tells you what? Anything raised to the 0 power is equal to 1. So this becomes a 1. Now, we also have 5 to the third and 5 to the 7th. This I can use the product rule on. We are multiplying the same base. Therefore, we can do what with the exponents? We can add them together. So this becomes 5 to the 3 plus 4 power, which becomes 5 to the 7th. Okay? Oh, hold on. I messed this up. It's not a 4. It's a 7. 5 to the 3 plus 7 power, which becomes 5 to the 10th. There we go. So we have 5 to the 8th over 5 to the 10th. You will notice that we are dividing the same base here. So we need to use one final rule. What is the name of that final rule where we're dividing the same base? If you're not sure, look through your notes right now. Once again, what is the name of the rule when we divide the same base? Quotient rule. Very good. So the quotient rule tells you the following. It tells you that you can subtract the exponents. So this I'm going to rewrite. Actually, I'll do it down here so you guys can see better. This becomes 5 to the 8 minus 10 power. 5 to the 8 minus 10 power, which is going to equal 5 to the negative second power. At this point, we have even one more rule to do, which is going to be the negative exponent rule. So we're going to take the reciprocal of this and get a final solution of 1 over 5 squared or 1 over 25. I will accept either of these two answers. 1 over 5 squared or 1 over 25. Okay? As you can see, there's a lot of steps involved here. And it's not that it's hard to do this. It's that you need to make sure that you're following the steps correctly, of course, and that you're keeping track of what is already simplified and what still needs to get simplified even further. All right, let's move on to number 6. 5 times 5 to the negative second. Let's go ahead and do the negative exponent rule here on 5 to the negative second. This is going to become 5 over 5 squared. This is quotient rule, so 5 to the first minus 2, which is equal to 5 to the negative 1 or 1 over 5. This, I will write this out. This is the quotient rule. This is the negative exponent rule. Okay? Getting a final solution of 1/5. All right. Number 7, 374 times 81 to the third over 9 to the negative third to the 0 power. Hopefully, you were able to notice one really big thing about this, and it's that everything inside of the parentheses is raised to the 0 power. So it does not matter at all what you have inside the parentheses. If it is being raised to the 0 power, then all of that is equal to what? To a 1. So all of this here is equal to 1. So hopefully you did not spend time trying to figure out what 81 to the third power is. It's a massive number. We get 374 times 1, which is equal to 374. That is your solution. And we're going to finish off with number 8. 15 to the fourth raised to the second over 15 to the seventh. This right here on the top is a case of a power rule. So that's 15 to the 8th over 15 to the 7th. We can do quotient rule on this. Quotient. Whoops. How do you spell this? Quotient. That's going to be 15 to the 8 minus 7, which is equal to 15. That's your final solution, 15. Okay. I believe that's it. All right. So these are all of the problems from the warm-up. Definitely you will see a question like number 4, number 3, number 4, maybe one like number 8 on the quiz next class. So if you are struggling to understand this, please go back to lesson 4.00. Make sure you rewatch the video, understand how these rules work to help you out for the quiz next class. Are there any questions before I move on? All right, so let's move on then to some guided notes. Now, exponential functions is something you guys have seen before. It's something you guys learned in IM1. And you learned about it through, just the basic graphing of it. This is the function that you've been exposed to, y equals a times b to the x. Sometimes it has parentheses, sometimes it doesn't. It does not make any difference. What is important to remember, though, is that b is your base. B is your base. So your base is the number that has the exponent. So you will never see a raised to the x power. It will always be b. And then, of course, like it says here, a is a parameter. So a shows whatever the a value is going to affect how your graph looks. Now, to review how parameter a and base b affect the graph of an exponential function, this is what I want you to do now, is you're going to go to student.desmos.com, like it's underlined here, and you're going to enter the class code CCHG96. This will give you access to the activity. We're only going to spend a little bit. I want you guys to mess around with the sliders so that you can kind of see how A and B affect the graph. You're going to write it on the side here, maybe just like one sentence for each. A does this, B does this. And in about 3 or 4 minutes, we're going to come back together and go over what these two letters or parameters are responsible for. Okay? So go ahead and do that right now. Okay, so as we can see, if we go to Desmos here, slide 3 has some questions. Just want to go over what you guys wrote. So looks like a lot of you guys understand that the parameter A is responsible for the y-intercept. Whatever your A value is, whatever the y-intercept is equal to. So that's the first thing. A lot of you guys wrote that. Then we have a second question. What happens when the parameter is a fraction between 0 and 1? Let's take a look. If I make parameter B a fraction between 0 and 1, then let's say I make this 0.6. What happens to the graph is it flips, right? Instead of going increasing, now it is decreasing. Okay. So once again, look, if I have something like 1.7, it's increasing. Remember that we look at a graph from left to right. So it's going from small, 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 it gets really, really big, right? Left to right, goes up. But then when I make it a fraction, now it starts to go down. It comes in from really, really big and starts to go down to really, really small. So that's what happens with a fraction. Then we have what happens when b is equal to 1. Well, if we make the base equal to exactly 1, then what ends up happening is that we have a straight line. Now, why do you think that is the case? If the base b is a 1, why do we get a straight line that is equal to 1? Think about what happens to 1 when you raise it to a power. What do you get when you raise 1 to any power? For example, 1 to the third power. What is 1 to the third power? 1. What is 1 to the 10th power? 1. What if I make 1 to the negative 5th power? It would still equal 1. So if your base is equal to 1, you guys, if the base is equal to 1, your answer will always be 1. So that's why we get a straight line when your base is 1. And then we have one more thing to answer. What happens when the base is negative? Well, let's see what happens. If I move the slider and I make it negative, then it looks like it's not even on the graph anymore. So the reason why this happens is because you cannot have a negative base. It is not possible to have a negative base because you don't get an output. So everything that we're going to look at is going to be positive bases. So anything greater than 0, of course. Okay? All right. So let's go back to the notes. And I'm going to have you guys write this down now. All right. So what did the graph look like when the base is greater than 1? Well, anytime your base is greater than 1, it will look like an exponential function. So it goes from really, really small to really, really big. So something like this. Please notice how I am graphing this. my graph is not allowed to cross the x-axis because I cannot have any negative outputs, right? It is not possible to get a negative output. This is what we just discussed about with the Desmos, because any number times itself, any number of times will always be positive, unless there's a shift. So when the base is greater than 1, we get a traditional exponential function that looks like this. When the base is a fraction, we said that instead of increasing, now we're decreasing. So we're coming in from really, really big and we're going to really, really small. Notice that as I graph this, I get really, really close to the x-axis, but I never touch it. I never cross it. If you make the mistake of touching the x-axis or crossing it, that would be incorrect. So don't do that. And then finally, we talked about what happens when your base is a 1. Well, it will always have an output of 1 regardless. It's a straight line that goes to 1. All right, so we talked about the parameter A. So parameter A is still the vertical stretch factor. It is still the vertical stretch factor. This is something that is consistent with all of the other different types of functions that we've looked at. It is responsible for making it wide or narrow. Base B can never be equal to 0, 1, or a negative value. Okay? So go ahead and write this down. I'll zoom out so you guys can see. Once again, parameter A is still the vertical stretch factor, and base B can never equal 0, 1, or a negative value. All right? Now, as it turns out, writing an equation for an exponential function is actually quite easy. You only need to know two things, right? Because there's only two parameters or two things in the equation itself. It's just A and B. So watch this. Write the equation of the exponential functions represented by the tables and graphs below. All right. So the very first thing is we talked about how A is directly responsible for the y-intercept. So you're going to look at the y-intercept. I'm going to highlight it in this case. The y-intercept is 0, 2. Whatever your y value is, that is the value of A. So in this case, 2 is your value of A. To determine your value of B, to determine what your base is, you need to determine the growth. What do you multiply 2 to get 6? 2 times 3 is 6. 6 times 3 is 18. Do you notice this pattern? To get to the next number, we're multiplying by 3. That is consistent. So your growth is equal to 3. Whatever your growth is, that is your B value. So to write an equation for the first one, we have y equals AB to the x. Let's replace these letters. Y equals A. A is your y-intercept. What is the value of y in the y-intercept? 2. So y equals 2. Parentheses. What is your growth? 3. 2 parentheses 3 to the x. And that is your solution. This is the equation that represents the table. Like I said, you only need to know two things. The growth and your starting value, or your y-intercept. All right, hopefully that seems easy for you. Let's try another one. Maybe this will really drive it home. Starting with the y-intercept. Once again, to determine a y-intercept on a table, you're looking at the point that is 0, comma something. So x needs to equal 0. So here I can see that x equals 0 and y equals 48. So that means that 48 is my a value. And I know to go from 24 to 12, you divide by 2. But we don't want division. This needs to stay in terms of multiplication. So how do you go from 24 to 12 using multiplication? You need to multiply by a fraction. So to go from a large number to a small number using multiplication, it involves the use of fractions. 24 times 1/2 is how we get to 12. 12 times 1/2 is how we get to 6. So my growth here is a half. I'm growing by a factor of a half, meaning essentially I'm cutting the next number by a factor of a half. When I write my answer, then, once again, I'm using the format y equals a times b to the x. Well, I know that a is 48. My starting value is 48. And my growth factor, or in this case, my b value, my base, is a half. So my solution is y equals 48 to the 1, or 48 times 1/2 to the x power. Okay. So I really want to emphasize the following. You do not ever, 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 ever divide. Do not divide. I know that to go from 12 to 6, you're dividing by 2, but we cannot leave it in terms of division. You have to write it as a multiplication problem. Okay, we are going to have... Actually, let me leave this one up to you. You go ahead and try C now. Go ahead and try C. You will notice that it does not have the y-intercept, so you do need to determine the y-intercept. All right, so you're going to have to work backwards here. Okay, so to go from 16 to 32, what are we multiplying by? By 2. It's obvious that this is a growth of 2. Now, like I said, you will notice that we don't see an input of 0. So we will need to work backwards to determine what the output is when x is 0. What is 16 divided by 2? 8. So we get the point 0, 8. This is your a value. It's 8. So when we write the following, we'll get y equals, when we're at the equation, we get y equals 8 times 2 to the x, giving us our solution. All right, letter D. So now instead of a table, we're given an actual graph. Well, if you notice, the points that we were given are the points -1, 81, and then we jump all the way to 2, 3. So there's quite a few numbers missing. All right, so we're missing 0 and 1. Okay. So we're going to kind of have to guess and check here. Figure out what is the growth factor to get from 81 to 3. Now, if I make, if I go straight from, okay, let's do 81 times 1 over 27. Sure, that'll get me from 81 to 3. But that's not, I'm going to be skipping these numbers here. So I don't want to do that. So why don't we start with something small? Let's say that our growth factor is 1/3 times 1/3. Well, 81 times 1/3, right? 81 divided by 3 is 27. So this is 27. 27 times 1/3 is, once again, 27 divided by 3, which is equal to 9. And then this does check out. 9 times 1/3 is equal to 3. So we have figured out that our growth factor is 1/3, and we've also figured out that our a value is equal to 27. By the way, this is a table, in case you haven't noticed. This is an x and a y table. So to write our equation, we get y equals, a is 27, b is 1/3 raised to the x. Okay. So with graphs, depending on what points you're given, you might need to make a table and work backwards or work like this. Okay. All right. Let's says here, go back to decimals and work through screens 5 to 13 to practice and investigate transformations. We will do that when we return from our break. You guys had some, practice with writing equations, and you had a brief, chance to look at new parameters like k and also the parameter h. So what can we say about h and k? How do they affect the graph? Good. So h moves things left and right. K moves up and down. So these are the same parameters that we've seen in the past, and they do the same things with this new function that we're looking at. So let's go back to the notes then and write a few things down. So once again, I'm just going to write some stuff here on the side. Please feel free to write this down as well. But we talked about how A is not only is it your starting value, but it is also responsible for the stretch factor or the vertical stretch factor. Then we talked about B. B is your growth. H moves left and right. And finally, K moves your graph up and down. Okay, so please write this down in your notes. It's like a summary of what we just looked at in the Desmos. And based on that, we can go ahead and do the following problems. So like it says here, parameters a, h, and k have the same effect on exponential functions as in all other functions you have already learned about. The biggest difference from all of the other functions you have learned in previous units is that the locator point is also affected by the parameter a. I'm going to highlight this. This is good information to know. But your locator point is going to be the following. So how do you figure out your locator point? Well, the locator point, h, is going to be h. That doesn't change. But k is affected by the parameter a. So to figure out your y value, it's the sum of a and k. That is how we figure out the locator point. All right, suppose we want to graph the function f of x equals 10, 2 raised to the x minus 3 power minus 5. First thing you want to do is you want to begin by graphing the parent function without any transformation. So we're going to begin by graphing 10 times 2 to the x. All right. Based on this equation that I'm given, I know that my starting value is 10. So I'm going to put 10 next to 0. That's my y-intercept, right? We talked about a being the y-intercept. Okay, now I know that the growth is 2. So to go to the next number, I'm multiplying by 2. 10 times 2 is 20. 20 times 2 is 40. 40 times 2 is 80. Going backwards, I'm dividing. 10 divided by 2 is 5. 5 divided by 2 is 5 over 2, or 2.5. Okay? So you want to begin by just simply writing out the table without any transformations. All right. So we're going to graph two graphs on this paper. First one is going to be your parent function, which I'll do with the information from the table. So 0, 10, 1 and 20, 2 and 40, 3 and 80. Going the other way, it's negative 1 and 5, and negative 2 and 2.5. We can connect the points. All right, and then don't forget, as we go to the left, you're going to get really close to the x-axis, but you're not going to cross it. So that is your original function. That is your original graph. So blue, I'm going to write here on the side. Blue is original. This does not have any transformations yet. This is where the transformations come in. So after you graph 10 times 2 to the x, then we're going to shift the function 10 times 2 to the x 3 units to the... If h is positive 3, then it's to the right. Now in this case, I know it looks like it's x minus 3, but remember that the minus is part of the equation. So the h is actually positive 3. So it's 3 units to the right. And 5 units to the bottom or down. 3 units to the right, 5 units down. So I'm going to change my... I'm basically going to go every point, and I'm going to shift it. 3 units to the right and 5 units down. Ready? I'm going to do it in green. So the point 380, I'm now going to shift that to 6 and 75. The point 2 and 40, I'm going to go 3 units to the right and 5 down. The point 1 and 20, 3 units to the right and 5 down. The point 0 and 10, 3 units to the right and 5 down. The point -1 and 5, 3 units to the right, 1, 2, 3, and 5 down. And then the point -2 and 2.5, 3 units to the right, 1, 2, 3, and 5 down. Connect the points now. Okay, so green is transformed. So the green graph is the transformation, where everything is shifted 3 units to the right and 5 units down. Your new locator point or your new starting value is now 3 and 5. Now, let me go back up real quick. Label the locator point. Remember that the locator point we find by using this that I highlighted in yellow. So H is 3. K is the sum of A plus K. Now, A is 10. So it's 10 minus, in this case, plus minus 5. So 10 minus 5, which is equal to 5. That's why this second number is 5. I'll do this here in blue, highlight that in blue, and then you guys can see kind of where that number came from. And then the equation of your horizontal asymptote follows y equals k. So it's whatever your k value is. Since in this case the k value is -5, then your new horizontal asymptote is -5. Now this is a new word, horizontal asymptote. You may not know what this means, so let me explain to you what an asymptote is. An asymptote is a value that you cannot cross or that you cannot equal to. We talked about how we cannot cross the x-axis. So in the original function, the x-axis or y equals 0, is your horizontal asymptote. We can get really close to it, but we can never cross it. As you make your shifts, whether you move it up or down, your new horizontal asymptote will revolve around the value of k. Since we shifted everything down 5 units, my new horizontal asymptote is -5. Notice how I'll do here in like a dotted line. Notice how now we cannot cross this dashed line equal to -5. So this right here, y equals -5, is your horizontal asymptote, or it's a value that you cannot have your graph equal to. Okay. All right. I forgot to write that down in this part. The original horizontal asymptote is y equals 0. We can see that over here. We cannot cross the y or the x-axis. I mean, okay. We can only get close to it. All right. We'll go over one more example, and then I'll leave one up to you guys. Are there any questions before I move on? Okay. Then let's move on to the next example. Consider the function g of x equals 2 times 3 to the x plus 2 power plus 5. Begin by graphing the original function without any transformations. In the original function without any transformations, a is 2, b is 3. So a is 2, our starting value is 2. And we are multiplying by 3. Maybe I shouldn't use an x. Let me use a dot. We are multiplying by 3. 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54, I believe. 2 divided by 3 is 2/3. 2/3 divided by 3 is 2/6, or 1/3. Sorry, 2/9. Not 2/6, 2/9. Okay. Times 3 times 3. Okay. The equation of the horizontal asymptote is always y equals 0 unless there's a transformation that moves it up or down. Okay, so let's graph this. This is in purple. We start at 0 and 2, 1 and 6, 2 and 18, 3 and 54. Going the other way, it's going to get kind of small here, but -1 and 2/3, -2 and 2/9. It's going to be really hard to graph it, but it's okay. All right. Okay, there we go. As you can tell, the original horizontal asymptote is the x-axis. Like I told you guys, that won't change unless you have transformations, which is what we're going to look at in the next part. Okay. So this, what I have right now, is the original graph. Once again, this is the original graph in purple. Now we're going to look at the transformation. So it's a transformation, an h value of -2 and a k value of +5. So this is going to make us shift 2 units to the left and 5 units up. 2 units to the left and 5 units up. Before I begin graphing the new one, I am going to write the locator point. So the locator point is h comma a plus k, the LP, h comma a plus k. That means that if h is a -2, it would be -2, parentheses a is 2, 2 plus 5 is equal to 7, -2 plus, or comma 7. That is your locator point. Right here. -2, comma 7. Oh, my bad. Other way around. -2, comma 7. There we go. Okay. Your new horizontal asymptote, we just shifted things up 5 units. So your new asymptote is y equals 5. Okay. Let me go ahead and show you the new one with a green color. So every point, you're going to move it 2 units to the left and 5 units up. So this point here, I'm going to go 1, 2 to the left and 5 units up. So 50, what is that, 54? Yeah, 54, 5 units up is 59, so about right there. This one is 2 units, 1, 2, and 5 units up, so about right there as well. This point, 1, 2, and 5 up is about right there. And then this point here is 1, 2, and 5 units up. It's about right there. And then we're going to get really close here. Connect the points, of course. All right, as we go to the left, you get really, really close to your new horizontal asymptote, but you cannot cross it. Your new horizontal asymptote is y equals +5. Don't forget to label your locator point. Your locator point is -2, comma 7, which is this point right here. -2, comma 7. Yep. All right. Once again, here the green one is the transformation. Green graph is the transformation. I'm going to zoom this out, and we are coming up on the end of this class. I'll give you guys the last 4 minutes to try the next example, and then I will put the solution up. So go ahead and take care of that. All right, here's a solution to this problem. So we have 0 and 20, 10, 5, 2.5, 40, and 80. Negative 2 and 80 is here. Negative 1 and 40. 0 and 20. 1 and 10. 2 and 5. 3 and 2.5. Okay. So we connect the points. So horizontal asymptote y equals 0. Shift to the right and up. New locator point is going to be 4, 35. New asymptote is y equals 15. And here's the new graph. So 4 to the right, 1, 2, 3, 4. No, 15, 1, 2, 3. 1, 2, 3, 4, 1, 2, 3. 1, 2, 3, 4, 1, 2, 3. 1, 2, 3, 4, 1, 2, 3. 1, 2, 3, 4, 1, 2, 3. All right, here's your new graph with the point 4, 35 as your locator point. Okay. We will finish the rest of this lesson next class. You will also have a quiz next class. Thank you.